Hi, everybody. My name is John Stanford. I am currently with a company called Solinia. Can you hear me? I got one person holding an ear. Okay. Good. Solinia is a startup. We focus on open infrastructure technologies. We have a lot of people who are doing interesting consulting around OpenStack and Kubernetes and Docker and DevOps and all these kind of things. I have a product team that's starting to do work in the product space around those technologies as well. A little bit of background. I have a LinkedIn profile. That's a good thing. And I've spent a lot of time doing software engineering, infrastructure consulting, DevOps, running SaaS platforms, and now lately this thing I just described. So what I've been doing lately has a lot to do with some of these technologies. I'm sure you'll recognize the icons on the left. We're shifting more towards the right, where we're getting into things like Kubernetes and Golang and Heka and things like that. It's been a very interesting and challenging shift, but we're doing it because we think it's the right thing to do for scale and the types of customers that we're trying to work with. So what I'm going to do today is talk a little bit about a use case that we've been working on as I try to figure out how to build products for large-scale environments when I have a lab that is like 7 nodes and being used for training and things like that. So we have a little OpenStack cloud, 1 controller, 6 compute nodes. We use it for R&D and training. It's shipping logs via Heka to a collector from each node, and then pushing those things into Elasticsearch. Very straightforward pipeline. It's doing a little bit of work filtering the data and trying to categorize things. But mostly what I want to figure out is, can I take this thing and scale it up to 1,000 nodes or 10,000 nodes, or what's the, where does it break? So, when the sales guys come in or the consultants say, hey, I've got customer XYZ, they have a 10,000 node cloud or Kubernetes cluster or whatever, can we take our stuff and drop it in there? And I'd like a better answer than the shrug emoji guy. So, which is what I give them today. Let's try it, let's find out, right? Let's start and work our way up. So as we go through here, we'll just kind of talk about what I go through in my mind when I try to figure out how to answer that question a little better. So every good recipe starts with onions. It's almost a universal constant. You'll have an onion in your recipe if it's a great one. So we'll start looking at this as how we peel an onion. So I took 7 days of log from our lab, and we have some very simple data points. About 25,000 messages per hour. There's an obvious pattern of square wave type of pattern. There's a couple dead spots in there and a couple spikes. And so, let's break it down a little further. If we look at what the traffic is doing from a server perspective, we can see that one server dominates all that traffic, and that's the controller. And so, that's 96% of the traffic coming in over a week, and 1% of the traffic is generated by each of the other compute nodes. And there were a couple nodes that weren't configured properly and just didn't make it into the cut, but they're probably not that important in the big picture because they're just like the other 4 that you see there. So they probably make up 1% of traffic. So when you break that down again by component, the OpenStack components, you see that Swift, the object store, is generating 60% of the traffic. It's really noisy, and probably overly noisy for what it is, but I'm not going to get into, should we go tune Swift? This is the environment I have to work with, so, this is what we've got. And beyond that, we've got Neutron at 25%, and then working our way down to other components. So that's an interesting thing to keep in mind. Next thing I wanted to do is look at the message rate. So Kibana is really good for some things, but at some point, you might want to start doing some aggregations that are a little beyond the visualization capability of Kibana, or at least the visualization capability that I could figure out with Kibana. So I switch over to like IPython or Jupyter or something like that, and I start writing little scripts to aggregate data. This is one of those. So I'm taking the 7-day, a query of the 7-day range of all the data in my database, all the log data that was generated by Heka, and I'm doing an aggregation called a date histogram aggregation on a per second interval across the timestamp field. And then I'm taking that data and I'm looking at it and going, okay, so what can I tell about this? I put it into pandas data frame and just try to get some statistics about it. So the interesting things that I see here are that, we've got 99.9% of our messages coming in at a rate of, no more than 64 messages a second. Okay, well that's not huge, so that's optimistic for my ability to scale things up. But then there's this outlier here, this recurring outlier that's much larger, 1,566 messages per second. And that actually occurred, maybe 10 times over the week. So it's not just a one-off thing. There's something happening in the environment that we may want to consider in our model. Okay, so let's look at that a little differently and put it in a histogram. I took out the outliers so it doesn't blow out the chart, but I haven't forgotten about them. I just wanted to be able to see the shape of this thing. And I've sort of taken it, I've hand-drawn a curve on there that looks to me like a pretty good fit. And I'll just keep that in mind as I go forward. So ultimately what I want to do is try to figure out how to generate messages somewhere along this curve as I try to simulate scaling this thing up. So the next thing I wanted to look at was the actual message sizing. So similarly, I'm going to do an Elasticsearch query. I'm going to do an aggregation. This time the aggregation is a percentile aggregation. I'm really just, it's not so much about time, so I don't need a date histogram. I want to see what my messages are, in size relative to each other. And so, another little Python script to put that in a data frame and describe it. And what I find here is that, my biggest message was 782 bytes. And 99% of my messages, well, let's say 95% because I use that number later, was under 240 bytes. This is great data when I want to build a simulation. So I'll do this again. I'll just put this on a chart and start to build a curve that looks like a reasonable fit for it. So let's sort of recap this and see what we've found out. We have an environment that generates roughly 25K messages per hour for 5 hosts that we're reporting, 1 controller and 4 compute nodes. We have a controller that's approximately 100 times noisier than a compute node. That's going to be interesting in the model for sure. I want to look at those very, very closely. We have one component that generates 60% of our traffic, and 99.9% of the time, there were less than 65 messages per second coming into to Elasticsearch. There's some traffic spikes that we'll want to think about, but they were very infrequent. I mean, they were beyond the 99.9th percentile. So that's something that we can set aside for now. We'll find out later as I go through what I ended up doing that I probably covered that just by the tooling I used. So and then 95% of the messages were less than 240 bytes, with a large one that's maybe 3 times that. Okay, so we've got a good set of data to start thinking about. And you pick up the cookbook and it says, hey, we've got a bunch of model parameters, we've got a bunch of statistical distributions, let's try and figure out which ones look a lot like what we're doing, and sort of pick those things and generate a curve that we can select samples from to simulate this data. And so we've got flow rate, we've got what hosts are speaking, we've got what components are speaking, the size of messages, content of messages, and then whatever else you can think of that seems like it might be relevant to the model. So that would be kind of step 1. Step 2, you might want to add some random noise, right? So you don't have these nice smooth curves. You may want to do things like, okay, well, my message rate, I'll select a sample off the curve. It's 10. I should generate 10 messages this second. How do I distribute them across the second? At every slice, every millisecond, I might make a quick calculation and say, is this one of them? Yes, no. Or did I generate 5 here? Whatever your model, you think is representative of real world for you, that's where this random noise stuff can help you out a little bit. So then finally, you just execute everything flawlessly and you get a Thomas Keller dish, right? It's fantastic. So your model is perfect. You can answer your question unequivocally, and you're done. You can just go sit home and wait for the sales to come in and know that you can handle, 100,000 node cloud, no problem, or not. So that's ultimately where you want to get to. So now here we are. This is what happens when you don't put your toque on, right? So your knives aren't sharp. You're not a professional data modeler. Your people are pounding for their forks and knives on the table, waiting for their meal, and you just got to get something out the door, and you have to answer a question. So you'll probably end up something like meatloaf, right? We can arguably agree that meatloaf is not horrible, but it's no Thomas Keller dish either. So it may be satisfactory, but we'll move forward and see how it goes. So let's revisit what we had to work with. We've got this environment of shippers and collectors and Elasticsearch. In my opinion, when I started this process, I figured where I was going to experience pain wasn't any of the individual shippers or the network between one of those and the collector. It's probably somewhere in the collector or Elasticsearch where I'll find my first bottleneck. So when I started my test case, I started looking at a plan of staying on the local node with the collector, flooding that process with messages, monitoring as much as I can around it, and then just keep increasing the message rate until something obviously breaks. And so there's this thing called Hekaflood. We'll get into that a little bit in the next slide, but Hekaflood just blasts messages at a Heka collector. How many people use Logstash? A lot. How many people use Heka? A few. I'm fairly new to Heka. I've found things to be pretty interesting over there. The flood utility literally just blasts messages at a Heka process, and you can control things like the message interval, the message size or max message size, and things like this. One of the things that I found missing is this late bind timestamp. So the first time I ran my Heka flood process, I'm like, okay, great. I just jammed like 2 million messages at my infrastructure, and then I ran my query against Elasticsearch, and I've got 1 bar with 2 million count on it. I'm like, wait a minute, what's going on here? So what was happening was that when Heka flood starts up, it knows kind of the profile of the flood job you want to run, and it generates a set of fixed messages. And in that fixed message, it generates the timestamp. So the timestamp for all your messages is exactly the same. And no matter how long you run it, I'm like, oh no, that's not going to do me any good for this conference. It is Saturday. I got to get this done. So I got down into code and made a flag, last bind timestamp, to say, okay, late bind timestamp, excuse me, to say, hey, look, I want the timestamp to be added to the message at the time you send it. I know this might be a little performance hit on the Flutter, but that's really important data to me. So I'll be doing a PR for that a little later, but it got me one step further in my cooking process here. So seems like a good idea. We're using Heka, might as well use its flood tool. The good part is I got control over the message rate. I can specify it in milliseconds or microseconds, whatever, and just say I want to send this many messages. The not so good was that you don't get a lot of control over the content of the message, and I think that's important in a model because that's what's going to help you decide whether your path through the rules of filtration of your messages is taxing the system more or affecting scalability, I guess you would say. So in this case, it's just generating a garbage string. It's kind of using maybe the same one or a few different ones for the whole show. That's something I would improve, and I'll probably try to work with the folks to incorporate some flexibility where you can select from a sample of messages or something like that. As we talked about, the timestamps were assigned at initialization. I've already fixed that. I'll work with them to get that back in. I couldn't get the variable message sizing to work. So when I ran the message size sample to see what the distribution of message size were, they were all the same. And I'm like, okay, well, the good and the bad is they were the same at about 1K message. So it's 4 times greater than my 95th percentile message. So, okay, it's not accurate, but it's at least conservatively large. So I may be able to glean some info from there. On a side note, I've found the community to be very helpful and friendly and receptive to code contribution and all that stuff. So, big props if there are any Heka committers in the audience. I'm very pleased to be working with you guys. Just starting, so you'll see my name on probably one pull request, so not too soon. So that's great. So what did we get? I'll give you two views. This is the light version of monitoring. I use Marvel and I use Kibana. And you can see that they look significantly different. So the first time I'm watching the Marvel data, and I didn't have Kibana up, and I was just sort of hoping to get Marvel. I'm like, well, it's delaying. I don't see, when I add a new flutter with another 1,000 messages per second, I don't see that hitting immediately. And then I'm just like, oh, wait a minute, it's doing a 10-second aggregation. So not only am I not seeing the peaks that I would expect to see, I'm not seeing the dropouts that I see in Kibana as well. You can really see towards 1640 or about the middle of the chart where we get into this rate where I'm sending about 5,500 messages a second to this one little collector and one little Elasticsearch node, that even Marvel starts to show a bunch of destabilization. So if you knew what you were looking for, that's not a flat line, and it probably indicates that something's a little wacky. Ideally, you would have a more fine-grained look at the data, which is what we got down in Kibana. And what you really see is that everything stops for several seconds in this process at that flow rate, and that's a problem, right? I mean, I know that I've hit some threshold that wouldn't be sustainable in a real-world environment. So I've kind of got a high watermark for what's reasonably safe to say that I can do in this particular configuration for throughput. And so what did we learn? We learned that we can do about a sustained 4 megabytes a second, or 4K messages per second. They're at 1K per message. We learned that the collector and or Elasticsearch was having some trouble at that point. I guess I would add in there that it could have been the system and it could have been the flutters, but they were all stopping. It wasn't just one. And so, my guess is that the collector or Elasticsearch, put the brakes on the system and all that. But when I did the message count about what the flutters thought they sent and what the Elasticsearch thought it received, we didn't drop any messages. And I was listening to an earlier presentation talking about UDP and at Pinterest, and I choose to use TCP because I don't like drop messages, and I'll scale until I can't do that anymore, and then we'll figure something else out. But we got everything through, and so that was great. So strategically, what I learned was that the load tool I'm using needs a little work to represent the kind of models that I'd like to do. And I was really intrigued by Adrian's presentation the other day about Spigo and some of the stuff he's been doing. That looks really phenomenal. I'm like, I wish I had that kind of tinkering time. Anyway, I'll hope to be looking into that one of these days soon. And the resolution of the monitoring tool is very important. We should be aware of what we're looking at and make the appropriate interpretations based on that. And then finally, I should prepare better for my presentation so I don't have to scramble and do this, like Saturday and Sunday, before the conference, because I made some assumptions about what the tools and all that would do. But anyway, on to our first model. So on to our first model. I'm going backwards again. Where did our first model go? There we go. On to our first model. Our intuition is that we could do about 4 megabytes a second, which is, when you do the math, about 17,000 messages at the 95th percentile, 240 bytes per message. We also had a starting 99th percentile, 99.9 percentile of 64 messages per second, which would be, at that message rate, about 265 controllers and 1,060 compute nodes if we scale up our starting point. And this is just literally a linear scale of what we did there. And that's using that sort of 1 to 100 ratio of compute node to, of controller to compute node. And so we just put that on a little chart. And so now, when the sales guys or the consultants come to me and say, hey, can we do, 2 250 controllers and 10,000 compute nodes, I can say yes. Oh, no, it's the other way around. Sorry. 100 controllers and 15,000 compute nodes, I could say yes. If I say yes to 250 controllers and 10,000 compute nodes, I'm no longer in that blue area, the shaded area that seems like to be safe from my model. But ultimately, the real answer is the model says it's okay, but we know the model has limitations. So what we really want to do is, find the real bottlenecks in the system and improve the model. So we don't know whether it was system resources or the data store, or collectors, or load generators, or whatever. And we also didn't extend that back to network and the systems that are generating data. So if I were to take this further, I would just make the model more robust. I would also look for tools that can support the type of probability distribution and sampling that I want to do to make it even more realistic, because there's no way I'm going to immediately have access to an order of magnitude larger cloud before I have to, answer one of these questions because a customer environment has come up where we have an opportunity. So I suspect that many folks are in this same kind of situation, even if you're in your own environment where you're talking about capacity planning and wondering where the break points and choke points are and all that stuff. So hopefully this was a nice introduction to doing that sort of modeling. Ultimately though, bringing real world data back into these models is important because it can help you either validate or refute the model itself. And if you get a refutation, then you've got work to do. If you validate it, you just know you weren't totally wrong. With that, since I have paid for this right to use Meatloaf, Meatloaf would like to ask you if you have any questions and say thank you.